Hey everyone, and welcome. Today we're going to pull back the curtain on one of the most fundamental rules in all of electricity, Ohm's law. It's this incredibly simple yet super powerful idea that really explains what's going on inside every single wire and circuit you can imagine. And trust me, by the end of this, electricity is going to feel a lot less like magic and a lot more like something you can totally wrap your head around. So let's kick things off with a question. Think about electricity like water flowing through a pipe. You've got some pressure pushing it, that's the push. You've got the actual water moving, that's the flow. And of course, the pipe itself might be narrow or clogged, creating an obstruction. So what's the one thing that connects all three of those ideas? Pressure, flow, and obstruction. Well, that's exactly what Ohm's law is all about. All right, here's our game plan. First, we'll hit the main law itself. Then, we're going to figure out why the actual shape of a wire really matters. After that, we'll dig into a special property that every material has. And finally, we'll zoom in for a closer look before we wrap up with the key takeaways. Sound good? Let's jump in. So our story starts way back in 1828 with a guy named George Simon Ohm. He figured out this beautifully simple connection that basically became the foundation for how we understand circuits. And he did this long before we even knew what an electron was. Pretty amazing, right? Okay, so what did Ohm actually figure out? He saw that there's a direct connection between two things. The first is potential difference, which we measure in volts. Just think of that as the electrical pressure or the push that gets charges moving. The second thing is current, measured in amperes, which is the actual flow of those charges. And Ohm's big aha moment was realizing that the more you push, the more flow you're going to get. It's a direct relationship. And here it is, the famous equation V equals I times R. Voltage equals current times R. Now that R is the secret sauce here. It's the number that tells us exactly how much a particular wire or component is fighting back against that flow. And that R, as you've probably guessed, stands for resistance. So resistance is literally the opposition, the obstruction. Going back to our water analogy, it's like a really narrow or rusty section of pipe that makes it harder for the water to get through. The higher the resistance, the tougher it is for current to flow. And we measure this in a unit called the ohm. Yep, named right after him, and its symbol is the Greek letter omega. Okay, let's make this real. Imagine you've got a standard 9-volt battery, and you hook it up to a little light bulb. You get out your meter and measure the current, and it reads 3 amps. So what's the resistance of that light bulb? Well, we just shuffle our formula around a bit. Resistance equals voltage divided by current. So 9 volts divided by 3 amps gives us a resistance of 3 ohms. See? Simple as that. So you might be wondering, where does this resistance even come from? Is it just a magic number? Well, no. It turns out that a huge part of resistance comes from the actual physical shape and size of the object itself. Geometry is everything here. To really get this, let's use this simple model. Just imagine this blue block is a piece of conductive material, like a chunk of copper. It's got a certain length, which we'll just call L, and has a certain thickness, or cross-sectional area, that we'll call A. Now, what do you think happens if we stick 2 of these blocks together end to end? We've just doubled the length the electricity has to travel. It's kind of like telling a runner they have to run 2 laps instead of 1. It's going to be twice as hard, right? Same idea here. The total opposition, the resistance, just doubled. And that gives us our first big rule about shape. Resistance is directly proportional to length. The longer the wire, the more resistance it has. Shorter wire, less resistance. Makes perfect sense. Okay, so that was length. But what about the width? Let's go back to our single block. What if we slice it right down the middle, lengthwise? We haven't changed the length, but we've cut the area for the current in half. This creates a serious bottleneck, like going from a 3-lane highway down to 1 lane. It's much harder for traffic to get through, and you guessed it, this also doubles the resistance. And there's our second rule. Resistance is inversely proportional to the area. A thicker wire is like a wide open highway, plenty of room, low resistance. A super thin wire is a traffic jam waiting to happen. Less space, much higher resistance. So we know that shape is a really big deal. But hold on, there's still a piece of the puzzle missing. I mean, think about it. A copper wire and a glass rod of the exact same size and shape are going to behave very differently, right? This is where the actual material itself comes into play. So when we put our 2 rules together, that resistance goes up with length and down with area, we can build the whole formula. And it looks like this. The resistance, R, is equal to the length divided by the area times this new symbol, the Greek letter rho. So what is this rho? It's called resistivity, and this is the key ingredient. Resistivity is an intrinsic property, meaning it's baked into the material itself, just like its color or how dense it is. It's a number that tells you how much that specific substance, copper, rubber, gold, whatever, naturally fights against electricity, completely separate from its shape. Let's just put these two side by side to make this crystal clear because this is a really important distinction. Resistance is about a specific object. It depends on what the object is made of and its shape. Resistivity is about the stuff itself. Copper has a very low resistivity. Rubber has an incredibly high resistivity. And that's the fundamental difference. Okay, so up until now, we've been looking at the whole wire, the whole conductor, the big picture view. Now we're going to put on our physics goggles and zoom way in to see how Ohm's law works at any single tiny point inside the material. This is the microscopic view. To even talk about this, we need a new tool. It's called current density, and we use the letter J. All it is the total current divided by the area it's flowing through. It basically tells you how crowded or concentrated the flow of electricity is at one specific spot. And this right here, this is what you could call the purest, most fundamental version of Ohm's law. Instead of the total voltage across the whole wire, we talk about the electric field, E. You can think of E as the strength of the electrical push at one single point. And this law says that the push at that point, E, is directly proportional to how dense the current is, J. And what connects them? You got it, our old friend, the material's built-in resistivity, rho. Now, a lot of the time you'll see this equation written another way. Sometimes it's more useful to talk about how well something conducts electricity rather than how much it resists. It's a glass half full kind of thing. So we define a property called conductivity using the Greek letter sigma, which is simply the inverse of resistivity. And when you use that, the law becomes the current density you get is proportional to the electric field you apply. It's the exact same law, just looking at it from the other side. Whew! All right, we have covered a ton of ground. We went from a simple idea to how shape plays a role and all the way down to the microscopic level. So let's just take a breath and pull everything together with a quick summary of the key formulas. Here they are, your whole toolkit. You've got the classic V equals IR, that's for the whole circuit. You've got the formula that tells you how to calculate resistance based on an object's shape and its material. And finally, you have the two microscopic versions that describe what's happening at any point inside the conductor. They all tell the same amazing story, just from slightly different angles. And that leaves us with one last, really fascinating thing to think about. We know resistivity is just a core property of a material. Copper is low, glass is high. But why? What is actually happening with the atoms and electrons inside copper that makes it an electrical superhighway, while the atoms in glass act like a total brick wall? Now that is a question that takes us even deeper, right down into the quantum world.